morning. We begin lecture 22 as always with a quick summary of lecture 21 and some overlap with the previous lecture because some students expressed any feedback saying that some of the mathematics was not very familiar to them. So we walk a tight line between spending too much time in the mathematics and also not doing any. So basically somewhere in between, so that we get enough hints to solve the detailed derivations, but at the same time making sure that we are getting the intuition. So this course will walk that fine line between spending too much time, and the idea is not to spend too much time in mathematics, though that is something that is a very valuable component. So let's start with a quick summary of lecture 21. We were almost at the point of completing our derivation of the BER of BPSK. We will take the last step and then spend a little bit of time understanding the asymptotic behavior. Asymptotic in the context of what happens at high SNR. So that sort of tells us what is the trend that each of these modulation schemes will give us. With that information, we'll be able to construct a bit error rate table of most of the, in fact, of the complete set of binary modulation schemes. So that sort of tells us, okay, this is the way to proceed, this is how we would compare, this is what the methods that would be followed. We will move from the context where we've been talking primarily about Rayleigh fading to some of the other environments that are very important to us. When there is the presence of a line of sight component. That scenario comes when we have a different distribution function for the received signal envelope. So no longer Rayleigh, but a new distribution which is referred to as Ricean, which turns out that it's actually a generalization of the Rayleigh PDF. In other words, the Rayleigh is a special case. So we can just make a note that Rayleigh is a special case of this. Rayleigh PDF is a special case of the Ricean. So it's useful for us to understand how to characterize the Ricean PDF, and today's class, a significant portion is going to be to understand how to characterize the Ricean, understand and interpret it in terms of the performance and its impact. This is a special case. So if the terrestrial wireless communications, cellular, gives us Rayleigh, give me a scenario that will give you Ricean. Not indoor. Indoor you already told me before. What else? I think I hear satellite, because which are the scenarios that you would have, like for example, if you're doing GPS and you're outside, outside of the buildings, there you will have a line of sight component. So this actually comes a lot of times in the context of satellite communication. So it's very useful for us to understand Ricean. As we will soon find out in the course of the lecture, the mathematical formulation of the Ricean PDF is not very amenable for us to do the BER analysis. So it turns out that the Nakagami M is a formulation which is an equivalent formulation which tells you the similar types of distributions, but which is more amenable for the analytical work. And in the process, we will also be using a tool called the moment generating function, which I'm sure you would have studied either in probability when you're looking at these different distribution functions or in digital communications. If not, we will just use the definitions here. Okay, so that's going to be the flow of today's lecture. As always, if there is a doubt or a clarification, please do not hesitate to stop me and ask for that. So as I mentioned in the last class, our goal is to get a good handle on the fading channel, both analytically as well as through simulation as well as through intuition. All three components are important. So let me just mention some of the points that we discussed in the last class. So we were talking about fading channels and why we were not able to use coherent in certain scenarios. So one of the things that we always remember in the context of fading channels is that we could have high Doppler. High Doppler means that we will have difficulties in channel tracking. that was what we have mentioned, and again we saw it in the context of differential detection, hybrid schemes, all of that, but the essence of it is there is the issue of high Doppler where channel tracking becomes difficult, and it may be advantageous for us to go ahead and use a differential modulation scheme. Okay. Now another element which tied to this is the following. If you remember, we said that if I want to do coherent estimation, coherent detection, I must get channel estimates. I must get them at least as frequently as the coherence time, because beyond that the channel will change significantly. So high Doppler is related to coherent time, and it's related to the coherent time in the sense that coherent time is decreasing. Okay, which means that my system design is going to have a impact which says that my repetition of the training sequence, the repetition frequency, how often I send, repetition frequency of the training sequence. The training sequence is a known sequence which is used for estimating the channel so that I can do coherent detection. This frequency will increase. What's the impact of this increasing? My overhead has increased, which means that my user rate is going to go down. Okay? Overhead is increasing, which means that user data rate, user throughput is going to go down. So you see that there are linkages, and it's not one without the other, and all of this. So if you could do coherent differential detection, or any other form of non-coherent detection which did not require the knowledge of the channel, notice that your system design is not affected by Doppler. You will not be spending any overhead on transmitting these training sequences. So there are several advantages, but again there are limitations that we would have to keep in mind. So this would also mean user data throughput will go down. Okay, so there are linkages to the system design, and I would like you to always keep in mind that the different trade-offs that are happening. Okay, the other element that we also mention is that fading, which occurs when we are moving. This will typically lead to burst errors, and burst errors are not very effectively handled by FEC. So therefore the use of an interleaver is to make the so we introduce the interleaver to make the data, the errors appear as if they are in random positions. So the notion of interleaver. So to randomize the, I will just say randomize the errors, randomize the position of the errors. Okay, what in the channel occurs as consecutive errors, but when it goes into the decoder will be in random positions because of the interleaver, de-interleaver that will happen. So basically this is interleaver coupled with a de-interleaver. Only then you will get the randomization. Okay, we didn't talk about the de-interleaver, but basically it's the reverse operation that happens. The other point that we discussed in the last class is that is the notion of the fading SNR. Basically, in AWGN, SNR is a constant, EB by N naught. When we talk about fading, it becomes alpha squared EB by N naught, where alpha is a random variable. Alpha has got a Rayleigh distribution. If you define gamma to be equal to alpha squared EB by N naught, then this gamma is the instantaneous SNR. Okay. So this gamma is a very, very important quantity for us. That's the instantaneous SNR. And it's a random variable. And we have shown that this gamma has got a exponential distribution. That's what we derived, but we'll just view that once more. Exponential PDF, it has exponential PDF. Okay, now since it's a random variable, we can talk about average SNR, expected value of gamma, and this we denoted by uppercase gamma, and we said that this will be equal to expected value of alpha squared EB by N naught. And if you have chosen your the variances of the real part and imaginary part of your complex channel gain to be such that they are, each of them should be equal to 1/2 sigma squared equal to 1/2. That means the variance of the real part is 1/2, imaginary part is 1/2. Then you will get the net variance of the 2 sigma squared to be equal to 1, and that means that your average SNR in the fading channel will be the same as the SNR in an AWGN channel. Again, this is the environment which we will do most of our comparisons. Then the next part of the maybe we can summarize this in the following manner. Let me just write it down, just for, since a few people said that this is not very familiar. Okay, so we have defined an instantaneous SNR, gamma. Instantaneous SNR, and this is equal to alpha squared EB by N naught, and we have said that gamma is equal to expected value of the of this random variable, and we have shown that if the alpha, f alpha of alpha is alpha by sigma squared e power minus alpha squared by 2 sigma squared, this is the Rayleigh. The envelope is Rayleigh distributed. The SNR f gamma of gamma is given by 1 by uppercase gamma e power minus gamma by gamma, where gamma is equal to, oh, I've already written that. Okay, so this is the exponential PDF. Exponential PDF. The other parts that we had also revised or derived in the process was the bit error rate performance of dBPSK. dBPSK in AWGN has a BER expression that is given by e power minus gamma, half e power minus gamma. We used the expression for the PDF to get the performance in Rayleigh fading. Rayleigh fading, the BER in Rayleigh fading, we got it to be equal to 1 over 2 into 1 plus gamma. Okay. And again, if the average SNR in an AWGN case, this would be equal to half e power minus gamma, because instantaneous and average are the same. So this is a very useful formulation. We derived the PDF of the SNR, applied it to get the BER of dBPSK in Rayleigh fading using, it's just a one-step integral. It was an exponential integral. Now I would like you to focus on how to do the high SNR analysis. Again, it's something that's very useful for us. So high SNR approximation or asymptotic analysis, sometimes we call it as asymptotic analysis. Asymptotic analysis basically says what happens when my SNR is high, high SNR. So which means my gamma is much greater than 1, because gamma equal to 1 is 0 dB SNR. That's not what we're talking about, a 20, 30 dB SNR, where gamma is much larger than 1. Okay. Now under the assumption that gamma is much larger than 1, 1 plus gamma can be approximate, it's gamma, can be approximated as gamma. So this actually can be approximated as 1 over 2 gamma. Again, it's a very simple approximation once you apply the interpretation that is available to us. This is a useful aspect, something that we add on to whatever we have done in the last class. And I believe this is where we left off the differential BPSK. We then picked up the, so that was the graph. We showed that the fading graph is going to be much worse. It's going to go linearly with a negative slope, and that is slope is equal to 1. And therefore, this is the scenario that we have derived with the BER analysis. Now we moved over from there to BPSK. And we wrote down the expression for the bit error rate in fading, which involved the Q function and the distribution of SNR. Again, we will use the SNR distribution. So that is the PDF of the SNR. We did the first step of integration by parts, and I hope you had a chance to complete the step that we had where we left off. And we showed that the integration by parts actually results in a derivative of an integral, and basically we should have been able to verify this. This is okay. Basically, we've been able to get 1/2. Okay, now what I would like to do is just give you the one more step before we get the final answer and begin and move forward from there. So there are two substitutions that we need to do for completing this calculation. So let me just give you an indication of those. So substitutions. Okay, I'm assuming you've reached up to this point. This is the expression for the probability of error of BPSK in fading, and we are one step away from the answer. So we're going to do the following approximation. Substitution number 1. 1 plus 1 by gamma, that's in the exponent. That's actually equal to gamma plus 1 by gamma. I'm going to write it as 1 over 2 sigma 1 squared. 1 over 2 sigma 1 squared. Now you may wonder why we are doing that. Let me explain it to you once we have completed the step. But before I do that, I must now tell you that we now have 3 sigmas that are present in our discussion. The first one, the different sigmas that are present. The first one is sigma naught squared equal to n naught by 2. What's that? That's AWGN. That is the additive Gaussian noise that is always present, even whether fading is present or not. So this is related to AWGN. Okay. Then there is a sigma squared which is related to the Rayleigh fading, the real and imaginary parts. Okay, those two are already there in our discussion. I am introducing a third one. This is only for convenience. This is only a substitution. There is no other element. This is only for the purposes of completing this integral. Okay, so it does not have an interpretation like the other two, but don't confuse it with the others, because then it will actually will not give us the result that we are looking for. Okay, so basically, if I were to write this down, I will get root 2 sigma 1 is equal to square root of gamma divided by 1 plus gamma. Square root of 1, okay. So that is one substitution. The second substitution that will help us complete this discussion is gamma equal to x squared. Now that may seem counterintuitive, because we went from envelope to SNR saying that that's an easier one, but actually for completing the integral, this actually turns out. So since I'm integrating with respect to gamma, I need d gamma. That's equal to 2 times x dx. Substituting for x, this basically tells me 1 over root 2 gamma, 2 root gamma. 1 over 2 root gamma, d gamma is equal to dx. Okay, so I'll just give you a minute just so that you are okay with the two substitutions that we have proposed here. Okay. Now, if that's okay, then please rewrite the equation. Rewrite the equation. So now we will get the probability of error expression as 1/2 minus 1 over root pi integral 0 to infinity e power minus x squared by 2 sigma 1 squared dx. Okay, I think you're already seeing why the substitutions were made and what that helps us with. Basically, this is of the form of the integral of a normal random variable. So we have the following result, which says 1 by root 2 pi sigma 1 integral 0 to infinity e power minus x squared by 2 sigma 1 squared dx. This is equal to 1/2. So actually, we will not perform the integral, but we will do a substitution. That's all. So basically, avoiding the step of integration. So as I said, we are already through with the result. So the final result says the probability of error of BPSK in Rayleigh fading has a very nice closed form expression, which is given by 1/2 1 minus square root of gamma by 1 plus gamma. Okay, it's just substitutions. I hope you will be able to do that without much difficulty. Okay, so that is our result. Now, I would like you to do the high SNR or asymptotic analysis also, because that is also very helpful, high SNR approximation. So, what you would have to do is make the same assumption that gamma is much greater than 1. This is the same as saying 1 by gamma is much less than 1. Okay. So, basically I would like to get an approximation for this. Let me again give you the first step and then request you to complete it. Square root of gamma by 1 plus gamma. If I divide numerator and denominator by gamma, I will get 1 divided by 1 plus 1 by gamma. Okay, I've just rewritten it. So, this can be written as 1 plus 1 by gamma raised to the power of minus half. Okay. Or you can treat it as 1 by square root, well, don't put equal to here, square root of 1 plus x, where x is a small quantity. And for that, we know the series approximation, and it's valid because gamma is much larger than 1, 1 by gamma is much less than 1. Please do the series expansion. Let me just give you the first 3 terms so that you can verify that. But I would like you to actually be sure that you are comfortable with this. So, this series expression can be written as 1 minus 1 half times gamma plus the series expansion goes as 1 into 3 divided by 2 into 4, 1 by gamma squared. It is an alternating series. The next term will be 1 into 3 into 5 divided by 2 into 4 into 6. 1 by gamma whole cubed plus dot dot dot. Because we have made the assumption that is a high SNR, I am going to ignore this, which is 1 by gamma squared. This is also I am going to ignore, and all subsequent terms I can ignore. So, what I am left with is only 1 minus 1 by 2 gamma. It is a high SNR approximation, and it is a fairly good one. So, the high SNR approximation, the probability of error of BPSK in Rayleigh fading under high SNR, I would like you to verify, comes out to be 1 by 4 gamma. Is also a linear slope. It is goes down with a slope of minus 1, but it has got a different constant with respect to differential BPSK. What is the difference between the two? A factor of 2, which means which is worse? Coherent BPSK or differential BPSK? Differential BPSK is worse, and the shift is going to be 3 dB. So, what we can do is now draw a graph which will be very helpful for us in interpreting this result. So, here is my bit error rate as a function of SNR. Notice that I can now write it in terms of the SNR as gamma or EB by N naught, average value. AWGN graph is going to be steep. This is BPSK, this is differential BPSK. So, this one is BPSK, the shift of 3 dB, and this is going to be differential BPSK. Okay. And why is DBPSK worse than BPSK? Because of the 2 noise terms, and that is where it is showing up. And this is assuming, making an assumption of, this graph is correct under the assumption of ideal channel estimation. That is, you have ideal channel reference for doing the detection. Otherwise, what will happen to your differential, to your BPSK? This 3 dB advantage will at some point be lost, where you will get an error floor, whereas the SNR of the DBPSK will continue to degrade. So, this is with channel estimation, with practical channel estimation. With practical channel estimation at high Doppler. Practical channel estimation at high Doppler. Okay, so we have the complete picture, good understanding of what the fading channel will do, what is ideal, what is high SNR approximation, and with high Doppler. Make sure that you mention this, because at low Dopplers the channel, the graphs will be exactly the same as what you have seen. You will be able to do the tracking very nicely with high Doppler. Okay, this is a good point to answer any questions that you may have. We have done 2 modulation schemes. Basically, this tells us that regardless of which modulation scheme you are given, once you know the bit error rate performance in AWGN, you can then generalize it to what will be the performance in the fading channel. Of course, there are little tricks in the integration, but nevertheless, with experience, you will be able to handle these things without any difficulty. Okay, any questions, any clarifications that will be helpful for the students? Okay, if not, let us now complete what I believe is a very useful table. So this is the BER table. BER table, it's got 4 columns. The first column is the modulation type. The second column is the probability of error in AWGN. Third column is probability of error in fading. Well, let me write it as Rayleigh fading. We have not talked about any other, I'll write it in red so that you will be Rayleigh fading. And this is the last one is the asymptotic analysis, high SNR approximation. What we are going to do is write down this table, which will answer all the cover all the modulation schemes that are binary. Okay. So the first entry that we make is probably the most useful entry, which says BPSK. And whenever we talk about BPSK, the modulation QPSK is also covered, because both of them have got the same BER performance in AWGN. And then there is a constant envelope scheme called minimum shift keying. That's also a binary scheme which is used in several modulation, several communication systems. So BPSK, QPSK and MSK, all of them have got the following expression, Q of root 2 gamma. That's the expression in AWGN. When we take the average SNR and express it in a fading channel, this becomes 1/2 into 1 minus square root of gamma by 1 plus gamma. I am deliberately using different values in AWGN and Rayleigh fading, because once you move to Rayleigh fading, this lowercase gamma represents instantaneous SNR, and the expressions that we get are based on average SNR. So again, it's deliberate. You could also write this, if you wanted to, as Q of root 2 gamma. There is nothing wrong. In the case of AWGN, instantaneous SNR and average SNR are the same, so no problems about that. And high SNR approximation, we just now derived. This is 1/4 gamma. Okay. Now there is another modulation scheme which is called coherent binary frequency shift keying. 2 frequencies, F1 and F2. The separation between frequencies is different from minimum shift keying. Minimum shift keying is the one that gives us the optimum performance. Coherent BFSK, slightly worse than MSK performance. This is given by Q of root gamma. Okay, Q of root gamma. That's the BER in AWGN. Now, do we need to redo the derivation for Rayleigh? Not really, because if the instantaneous SNR is divided in half, the average SNR is going to get divided in half. So basically this can be obtained using the following substitution. You take gamma and replace it with gamma by 2. That also tells me that average SNR in the previous expression will be replaced by gamma by 2. So if you do that, this will come out to be 1/2 minus 1 minus square root of gamma by 2 plus gamma. Okay. So basically this is substitution. And of course you carry over the analysis all the way to the high SNR side, replace gamma with gamma by 2, this will become 1/2 gamma. So this is actually the asymptotic analysis says that this family of modulation schemes are actually shifted by 3 dB. But we know that already differential BPSK also is in the same location. So third one, differential BPSK. Differential BPSK. This is 1/2 e power minus gamma. That's the expression for the BER in AWGN. We have derived the probability of error in Rayleigh fading as 2 into 1 plus gamma, and the high SNR approximation turned out to be 1 over 2 gamma. And then the last one of the binary modulation schemes that we have is non-coherent binary phase shift key, BFSK, and that has a BER performance which is given by e power minus gamma by 2. Do the same substitution method, I do not have to redo the calculations. This comes out to be 1 over 2 plus gamma, 1 over 2 plus gamma, and of course again substituting gamma with gamma by 2, this comes out to be 1 over gamma. Okay, so this is basically all the binary modulation schemes that we have. Of course, GMSK is not there. I will show you in a minute how to get the expression for GMSK. But before that, all of the standard modulation schemes, coherent, non-coherent, all of them are on this graph. Any questions? Okay, so let's move to the previous graph and then say that okay, BPSK is correct. Also add QPSK and MSK, all of them have got the same performance. This is the graph of differential BPSK, it is also the graph of coherent BFSK. And then there is a third graph which is also shifted by 3 dB, another 3 dB, and that is the graph of non-coherent BFSK. Okay, so all the modulation schemes. So if you were to look at it in terms of the in the table, this corresponds to entry number 1, this corresponds to entry numbers 2 and 3, the last graph corresponds to number 4. So two of them have got the same asymptotic behavior. So there is a little bit of variation in this region. You have to actually plot the functions to see how they get. The asymptotic analysis is applicable in the high SNR region. Okay, so this you would have to plot using the expressions. What I have done is not correct. You have to actually plot it using the expressions. Okay, so again, keep in mind that this is the. So it's good for us to have a picture of what happens with Rayleigh fading. How do we deal with Rayleigh fading? What are the characterizations? How do we get the SNR approximations? And then also be able to do the high SNR approximation. Any questions on what we have done? Okay, always good for us as engineers to have a feel for the numbers. Okay, now if I were to be given that the average SNR in a AWGN channel, gamma is equal to 7 dB. This is approximately 5.012. What is the probability of error in the AWGN channel? Probability of error of BPSK in the AWGN channel is given by Q of root 2 gamma, which is Q of 3.17. You can either look at the table or the calculator. So using the Q table or the Q calculator, you can get the expression. Important thing is to get what is the order of magnitude. We are talking about 8.4 into 10 power minus 4. This is very good, 8 bits out of 10,000 bits. That means most of your frames of 100 bits duration are going to go through without any error. So this is a very good performance, very easy for us for FEC to make it almost error free. Now same SNR, if I were to be asked to operate in a Rayleigh fading channel, probability of error of BPSK in Rayleigh fading. Again, useful for us to get a feel for it. You can substitute in the expression that we have, but I'm going to use the approximation of 1 over 4 gamma, okay, and you can verify. This is approximately 0.5, 5 bits out of 100. So which means that this is quite an error prone channel. The same channel on average in the AWGN case was giving you almost error free. Now you have a, so the performance of Rayleigh fading is significantly worse. So let me just write it saying it is significantly worse. So this is something that we always have to keep in mind, that we need to make our design sufficiently robust when we are working in a significantly worse than AWGN. That is something that I always want you to keep in mind, that the minute it becomes wireless and you have multipath and you have Doppler, you say, okay, now I need to re-look at my system design, because this is an important element. Okay. Another useful aspect that I always want to keep in mind is, what if you don't have the Q tables availability, or you don't have the Q function calculator with you. So as engineers, we also always have approximations for the Q tables, approximation for the Q calculations, which basically says that Q of Z is upper bounded by 1 over root 2 pi e power minus Z squared by 2 divided by Z for large values of Z. Okay, and again, most of the time we may be interested in the high SNR analysis, so the argument of the Q function will be something which is greater than 1 for large values of Z. Please do verify that if I substituted at Z is equal to 3.17, this would have told me that my bit error rate is 8.3 into 10 power minus 4. The Q function told me it was 8.4 into 10 power minus 4. It's almost a negligible difference. So again, keep this in the back of your mind, that there is a good approximation for the Q function if you do not have access to the tables, and useful for us to work there. Okay. Any questions? All right. To summarize, Rayleigh fading means no line of sight. Now comes the question, what happens if I happen to have line of sight component present? How is it going to affect my statistics? How is it going to change my BER? How is it going to affect all of the analysis that we have gone through? So what we will do is just give you a flavor for what are the aspects that we need to work with, and then we will draw the intuition from there. So we are going to look at the following aspect. Let me give you the type. It is the distribution where there is line of sight component. So it is going to result in a different PDF. It's called the Rice PDF, after the famous communications engineer Rice. So sometimes we call it Ricean PDF, or we may even spell it as RICIAN. All are okay, Rice, Ricean, all of it is okay, but ultimately it basically covers the case when there is a line of sight component. So X comma Y are IID Gaussian, just like in the case of the Rayleigh PDF, no longer zero mean, but with means M1 and M2 respectively. Why is that? Because if the Gaussians are zero mean, that means on average your expected value is going to be 0. But if you have line of sight component, no matter what happens to the fluctuating component, the line of sight will always be present. So which means that there is a non-zero component at all times, which is captured by the means that are present. Now the means don't have to be the same, but in many cases they will turn out to be that the means are the same, but M1 and M2. And they have a common variance sigma squared. Common variance sigma squared. Okay. Now then we want to look at the envelope, which is defined by square root of x squared plus y squared. Then we are told that this has a Ricean distribution. the envelope will have a Ricean distribution, which is different from that of the Rayleigh PDF. Okay. Now, very quickly, I would like to cover some of the background information. Again, the idea is not to spend a lot of time in the mathematics, but it's important for us. Please refer to Proekis Digital Communications Chapter 2, where the Ricean PDF is derived, and it is the complete description is given for us. But we will cover it to get to the insight. So here is the important aspects of the description and the process that is given for us in the Proekis. So expected value of x is equal to m1. It's no longer 0. Expected value of y is equal to m2. Now the variance, expected value of x minus m1 whole squared, this is equal to expected value of the variance of the x and the variance of y minus m2 whole squared. This is, both of them are equal to sigma squared. So that tells us that expected value of x squared is going to be equal to sigma squared plus m1 squared. Again, these are results that you will easily be able to verify. And expected value of y squared is equal to sigma squared plus m2 squared. Okay. Now comes a very, very important why this is the difference between Rayleigh and Ricean PDF. So expected value of v squared is equal to expected value of x squared plus expected value of y squared. Again, like before for the case of the Rayleigh case. In Rayleigh case, this was equal to 2 sigma squared because the means were 0 mean. So now what we will get is sigma squared plus m1 squared, and this one is going to be sigma squared plus m2 squared. This will be 2 sigma squared plus m1 squared plus m2 squared. Okay. And we know from before that this part is what contributed to the Rayleigh. So this is the non-line of sight component. Basically, now you have a line of sight component and a non-line of sight component, and this is what covers the line of sight component. Notice that m1 and m2 are non-zero values, and therefore there will be some contribution due to this in the case of the Ricean distribution. Okay. So this is a very important element. Now, how do we characterize this type of environment? Rice proposed using something called a Rice factor. Rice factor is a ratio of the two. It's given by the constant k, uppercase k. This is given by these. If you call this, the notation used in the Ricean distribution is called as s squared. K is defined by the ratio of s squared by 2 sigma squared. Okay. So it is nothing but the ratio of the power in the line of sight component, power in the LOS component divided by the power in the non-line of sight components. Okay. And most of the time when you are dealing with Ricean distributions, you probably would have encountered that is always given in dB, which is 10 log 10 of s squared by 2 sigma squared. It's always given in dB. That's usually the practice. They say, okay, it's a Ricean channel with 8 dB, k equal to 8 dB. So the interpretation is the following. Okay, very important. What happens when s is equal to 0? Special case. S is equal to 0 means m1 equal to 0 and m2 equal to 0. K will become 0 and you will get Rayleigh distribution. So this means you will get Rayleigh distribution. Okay, we should verify that. Okay. Now the next few minutes, that's what we would like to do. Very quickly look at the interpretation of the PDF. So as I mentioned, the goal is not to spend a lot of time in the mathematics, but hopefully the insight that we have already obtained tells us. So go back to our description. So if this is the scenario, x comma y IID with Gaussian with means m1 and m2, common variance sigma squared, v is equal to square root of x squared plus y squared. This PDF is given by f v of v equal to v by sigma squared. There is a Bessel function that comes in I naught times s, where s is equal to s squared is equal to m1 squared m1 did I say m1 squared plus m2 squared. I hope I wrote it as s squared. Yeah, s squared is equal to m1. So s times v divided by sigma squared e power minus v squared plus s squared by 2 sigma squared. V greater than or equal to 0, s greater than or equal to 0. S is the s squared is equal to m1 squared plus m2 squared. So therefore, s is a positive parameter and v is the envelope of the signal, again a positive parameter. So s squared is equal to m1 squared plus m2 squared, and I naught of the argument is a 0th order Bessel function. Again, does not matter. It's a function that is well defined. It's a 0th order modified Bessel function. Modified Bessel function of the first kind. Bessel function of the first kind. Okay. So the derivation is given to us in Proikis, and again time permitting, or maybe as part of an assignment we will work out the derivation of this. Again, not difficult, though you may say I've never seen 0th order Bessel function, leave alone modified Bessel function. I have no idea what it is. Doesn't matter. Don't worry about it. It's something that we will handle without any difficulty. So the definition of the modified Bessel function is just an integral function. Just if you have handled q, this is like the q function. Okay, it's 1 over 2 pi integral 0 to 2 pi e power z cos u du, and you can do the integration from 0 to pi, or you can do it from minus pi to pi. Both are okay, equivalent distribution. Again, it's an integral form of a variable. Okay, so basically this is the. So now the one thing I want you to do is very quickly substitute k equal to 0. K equal to 0 implies s equal to 0. If I substitute s equal to 0, what I will get is f v of v is v by sigma squared I naught of 0 e power minus v squared by 2 sigma squared. Easy to verify that I naught of 0 is equal to 1. So therefore, what we get is the Rayleigh distribution. Rayleigh distribution. Okay. Now, very important, before we conclude, to see what the Rayleigh Ricean PDF looks like for different values of k. Now, Rayleigh, we know what it looks like. Basically, it is highly concentrated towards the lower amplitudes. It hits a peak at equal to sigma, and v is equal to sigma, and then decays. There's a long tail, but these are the worrisome thing is that this is going to be where the problem is going to lie. Now, if I introduce a line of sight component, what happens? The line of sight component is always present, even when the non-line of sight component becomes very small. So therefore, the likelihood of the envelope being slightly larger it sort of shifts to the right. Okay? The stronger the line of sight component, the more it is going to shift to the right, because it's not going to look like the Rayleigh. It is going to look more and more, it's going to look different from that. Okay. Now, this is a graph that we will generate through a MATLAB assignment, but please do that By the way, several people have asked for postponement of the assignment. I have no problems with postponing the assignment, except that things are going to bunch up, because we're going to do a number of computer assignments and written assignments to keep in track. So as much as possible, keep up with the assignments. If you need extension, not a problem. So this is one aspect that I want you to keep in mind. The second one, which I hope will give you a lot of insight, forget the three lower graphs. The first one is Rayleigh distribution. You will have to, when you go back, you will have to draw this line. That line basically says that is your average received signal level. Okay, and you can see that's the type of fluctuation you will see when it is a Rayleigh distribution. Remember the three Ricean distributions that we looked at, take the last case, k equal to 10. So which means that there is a line of sight component which is strong, and there is a non-line of sight component. Now draw the graph. You can see that the fluctuations about the mean level have significantly reduced. So your BER is going to be much better than a Rayleigh PDF. Okay? So this is the insight, that once you move away from non-line of sight to having even a small line of sight component being present, you will see that there is a improvement in your BER performance. So a lot of insights that still need to be obtained from the understanding of the Ricean PDF, but by and large most of it will be through assignments. I hope you've got the basic handle of what happens when the line of sight component is present. We will build on this very quickly and then draw more and more insight from the performance in a Ricean system, and then how to interpret it in terms of our system design. Thank you.